Today we're going to use the geometric distribution and calculate probabilities and statistics for the number of tries before successfully flipping a water bottle. And I don't know if you remember the bottle flip craze. Could you do a bottle flip? Congrats to our football team for making the playoffs. I heard it was close, but you got it in overtime, so congrats. Next class, you will have a quiz, binomial and geometric distributions. Don't worry, I will have a review as normal. Now, today we are going to be doing a Peardeck in class. So if you were the class where I'm there, we're working through it together. And if you're the class on election day, you have a substitute, and this video will help you get through it. D1 and D4 reflections are open for full credit through tonight, tonight being the day of class. So A day, that's on Monday, and B day, that would be on Tuesday. So this unit, we learned about these probability distributions. You have here the discrete random variables that we started with, and there's the expected value and standard deviation. We also learned about binomial distributions last time, and in the last set of notes, you would have learned, and we have, if you did the reflection, you should have gotten some practice with this NP and square root of n times p times 1 minus p. It's not very difficult. It's pretty basic calculations there. And today we're going to be working with the geometric distribution primarily. And there is no staplet for this, but the formula is pretty simple. There are no combinations to calculate. And there is the formula for the mean and for the standard deviation. Now, all these formulas are on the math chart, the laminated math chart, so they are available whether you're testing or quizzing all year long.
He's the guy who created a global phenomenon. But now he wants to apologize as the backlash against the bottle flipping craze grows. The stunt looks pretty simple, as you can see in these YouTube videos. You toss a bottle with a little water in it, and you get it to land upright. Duke University basketball player Chase Jeter showed how he's mastered the technique. Kelly Ripa had a little problem with her toss.
Oh, nice try.
Here, a teacher tries it out. I found out myself, it's not as easy as it looks. Trying again, but eventually, 13th try. But some schools now want to ban the bottle flip craze because they say it's distracting students from their work. The Wall Street Journal just called bottle flipping really annoying. This is what started it all. Michael Senator gives the world's first ever demonstration at a talent show at his high school in Charlotte, North Carolina earlier this year. His video has been viewed more than 6 million times. 18-year-old Michael showed us how he perfected the technique.
I like to build to a 1/3 level, and then I flick it down my finger right here. And so I just flick it, land it, and then you can just keep doing it.
But he has this to say to ticked off educators who see bottle flipping as yet another diversion off school.
I want to apologize to all teachers. This was not my intention. It's not my intention at all to get your kids distracted. I can only imagine hearing the sound of it all day. I mean, that is one of the most annoying sounds in the world.
Okay, now you saw the video for how many bottle flips to go viral, and you should be working on the Peardeck part. So, the senior talent show is scheduled to take place this afternoon. Michael Senatori is in stats class practicing his act, bottle flipping. He tells his friends that the probability of successfully landing the water bottle right side up is 20%, 1 out of 5. Assume that each water bottle flip is independent. If he flips the bottle 10 times, how many do you expect to land right side up? Justify. Well, if we know 10, that's the total number of attempts. Then we know n equals 10. That tells us we're using the binomial distribution. And the mean from the formula chart is, or expected value, is n times p. So we have 10 attempts with a probability of 0.2. We expect him to get 2. And you could probably intuitively figure that out. because 20% of 10 is 2. So that's pretty straightforward. What is the probability he makes exactly 2 flips? Well, that one's a little bit more complicated because you got to figure out, okay, he's going to get 2 successful. He's going to miss 8. But how many ways can he get 2 successful? So you have this 10 choose 2. You should go ahead and write it that way. And let's see, 10 times 9 is 90, 45. This is actually 45 right here. But anyways, you could calculate it by hand. You could use the calculator. Remember, this is PDF because it's a binomial probability distribution function when we're talking about exactly. And so it's binom PDF of n equals 10, p equals 0.2, or x and x equals 2, and you get 0.3020. What's the probability he makes less than 2 flips? Well, then that means the sample spaces he can make anywhere from 0 to 10. Less than 2 would be 0 and 1. So go ahead and write out the formula. I would like to see this on your quiz next time, so go ahead and write it out today. You can actually, I want to see it on the Peardeck, but you can copy it down onto your notes if you like. And then, again, the shortcut for an at most 1 is CDF, and is 10, p equals 0.2, x equals 1, and you get 0.3758. Then they ask, what is the probability he makes at most 2 flips? So we could rework the problem we just did, 3, but now we're going all the way up to 2, so you can see that. Or you could say, hey, we already did 2 up here, and we got 0 and 1. I could add these 2 together to get the 0.6778. After the first 10 flips, Michael wants to do 10 more, but his teacher is getting annoyed with all the noise and tells him he must stop flipping once the bottle lands right side up. So we no longer know the number of attempts he gets. It's only until his first success, and this is a geometric distribution. The probability is still 0.2. So find the probability he lands it on the first try. Well, it's just 0.2 to the 1. That's it, right? Because he has a 20% chance on that one flip. So the probability he fails on the first try and lands on the second try is 0.8 to the 1, because we have 1 failure and 1 success, and you multiply it out. He fails the first 2 tries, and he lands it on the third try, so you have 0.8 squared times 0.2, and you get the 0.128. And then finally we do the fourth try, 0.8 to the third times 0.2 to the 1 is 0.1024. Now you could also do all these with geometric PDF, and you just would define p equals 0.2 and x. There is no n because it is not a fixed number of trials. So I guess that's the nice thing of bins is you have that n for binomial distributions, and you can think of it, oh, if I don't have an n, it can't be binomial. So we're going to look at the number of flips it takes for Michael to land the bottle right side up, and we go ahead and we fill in the table with those answers, and we can actually, let's see, we worked up to 4, right? And then you could do the binom PDF with p equals 0.2, x equals 5, p equals 0.2, x equals 6. Now, find the probability that he lands it on the 10th try, and it's 0.8 to the 9th times 0.2. So here, this activity, if you hadn't already learned the formula for the geometric distribution, you could kind of intuit it. In other words, it's sort of intuitive that you just take the number of tries and you have failures up until that last try. So the last try is successful, and then you have all these 1 minus p's to the number of tries minus 1. So k stands for the number of tries. Now, how many flips do you expect it to take for the bottle to land right side up? Well, the formula for the mean is so we expect him to get it 1 out of 5 times. So how many flips do you expect it to take for the bottle to land right side up? So 20% probability of landing. So we expect he lands 1 in 5 tries. And so we would expect 5 tries before he gets a successful one. And if you do 1 over 0.2, guess what? You get 5 tries. So that's the intuitive logic of it, and there's the formula to it. So geometric distribution, some big ideas that you want to write down in your notes is geometric setting, B, it's binary, I is independent, T is trials until success, and S is same probability. And I'm still keeping my pet peeve. I think S and I are pretty much the same thing. I'll have to talk to some stats gurus to say, okay, tell me what's really different about these two, right? And there's your geometric formula that is on your math chart. And it is always skewed to the right. It's always sort of exponential decay looking because you're going to have your highest probability. Look, let's go look at that distribution table. We start with 0.2, then it's 0.16. Why is that? Well, we always have this probability to start with, right? And we keep multiplying it by a number that's less than 1, and we keep doing that more and more and more, and that makes it always go smaller. So that's the intuitive sort of the why does this look like it skews to the right. The center, the mean or expected value is 1 over p, and standard deviation is square root of 1 minus p over p. All right? Now, let's go ahead and do some practice to check for understanding. Mason never has a pencil when test day rolls around. I had a student like that. I would take a pencil to his house, believe it or not. He started bringing a pencil after I did that. That was way back when I taught at Taylor. Anyways, because the classmates are tired of having to supply pencils for Mason, only 15% of students will give Mason a pencil when asked. That's kind of funny. Today is test day, and Mason begins asking randomly selected students for a pencil. Let y equal the number of students Mason asks until he finds someone who will give him a pencil. Oh, funny side note to that true story where I took the kid a pencil. The next day he comes to school with that pencil, and his name is written on it in Sharpie. He did not want me to go back, which is fine. Mission accomplished. All right, so let's describe this probability distribution. Be sure to check the appropriate conditions. So success is he gets a pencil, failure is no pencil, definitely binary. Trials are independent. They told you that they're randomly selected students, and it doesn't seem to be any dependency between one or the other. T, Mason asks until he finds someone. He's not going to keep asking for pencils after he gets a pencil. And they might look at him funny if he did. And probability is the same. It's always 0.15. All right? And this is a geometric distribution. So what is the probability the third person asks is that the first person who gives him a pencil? Well, that means he's going to fail twice. Poor Mason. 0.85 squared times 0.15. He's lucky, and it's 0.1084. What is the probability that Mason gets a pencil by the third person he would ask? So what that means is he gets lucky on either the first, second, or third, and we can just add up these probabilities. There's no overlap in them. And the geometric cumulative distribution function will add all these up. So it's just like the binomial cumulative distribution function. And so p equals 0.15 and x equals 3. And there you go. If you put that into the function, and you're going to need to do the calculator on this one because there is no staplet for this, or you're going to have to calculate it by hand. Both of them, you need a calculator either way. Anyway, so you get 0.3859. All right. So that would be, now ideally I still would like to see this written out and added up. Okay. Part D, how many people should Mason expect to ask before getting a pencil? We use this expected value as 1 over p. 1 over 0.15 is 6.67. Should Mason be surprised if Mason didn't receive a pencil until he asked at least 10 people? So that means, what is the probability that his success is 10 or higher? In other words, first 9 people refuse him. So what we're going to do here, since we can't work out to infinity, I'm going to calculate the probability that he's successful on the first 9 people, which is this geomet CDF with 0.15 and x equals 9. But this is the opposite of our answer, and it's 1 minus that. And when you do all of these probabilities and you figure it out, or I could calculate them by hand, but that's 9 calculations. No, that's technically 10 calculations because you got to do 0 through 9. So better yet, do geomet CDF. And that's second distribution function, guys. Make sure you know how to do it. Equals 0.2316 after you subtract all that from 1. Since 23% is not that unusual, he shouldn't be surprised if he has to ask at least 10 people. It won't happen all the time, about 23% of the time. So find the standard deviation for the distribution of the number of people he asked for a pencil before finding someone who will give him one. And so we plug in 1 minus 0.15 over take the square root over 0.15, and we get 6.146 people, which means we expect the number of people he has to ask to typically vary by 6.146 around the mean of 6.67 people. So on average, we expect him to ask almost 7 people before he can get a pencil. All right, and that is all on the Peardeck. Please don't forget to hit submit after you finish. I want you to get credit. This is an easy, free daily grade. And next class, you have your binomial distribution and geometric distribution quiz. And D1 through D4 reflections are open for full credit through tonight. So take advantage of it. Don't get a late grade. Get full credit.